use the file, the output file. It's like error seems null or something.
Okay, it could be that the file name was not really specified correctly, but maybe Kenneth can help and look there. Right, so let's go to the lecture 5 now, which complements actually our lecture 4 in several ways. We have firstly established the maximum margin classifier, which was a very smart way of basically saying we want to have a big buffer zone, right? The maximum margin furthest away from my samples that are there. However, the problem that we had is we assumed basically linearly separable data, right? And with this, we have now the trouble that in practice, mostly this is not the case. So we can now think about of extending support vector classifiers then to actually satisfy them. So the second part I would like to show is basically that the regularization aspect that you have discussed basically as part of the overfitting is something where we basically have to think about now how that fits in the SVM case, right? And it has a direct relationship with violations of the margin, with, let's say, some of the samples we previously discussed going over, right? Outliers being on the wrong side, contributing to this nonlinear separability property. Right, so let's look how we go to do this by just maybe quickly review the last lecture. The classification challenges by now I think pretty clear. We see that nonlinear separable data is contributing. Overfitting we discuss now again and again. Now regularization will be a cure. But take away the message in practice. You have also this when you come to an application domain. When you go to industry and have a real job. Scalability issues, high dimensionality on the data sets. So it will be not always that easy like those that are here prepared in the tutorial. You are responsible of taking the feature selections, right? You are the responsible of getting the data right. So all of this will be things where you tackle then these kind of aspects perhaps, or have to fight with, terabytes of data and select those out of the data that you need for data analysis. So lots of other challenges, but these are the two that are directly related to our modeling and to our machine learning. So it's the most interesting, and of course the most one we will cover here. We now look on the maximum margin classifier. You would say that, again, we talked about very many of these lines exist. We know that already, and we had to find interesting solution, really how we can get this now in a mathematical established way. We see it's a constraint optimization problem that we solve with a Lagrangian, and with this we could go to the mathematical toolbox using a tool for quadratic programming. And this is something which is implemented in the libSVM tool, so we don't have to carry all of this machinery on our own implemented. We just use what's existing in the libSVM tool. And this goes for both, actually. In the serial case, it's libSVM, and in the parallel case, we also adopted the algorithms inside the libSVM, just created it in parallel, right? So there's a little bit more than substance to it, but it's not part of this tutorial to have just parallel programming teach with MPI and stuff like this, right? But of course, they both follow the same, let's say, sequential minimal optimization steps in the training process in order to get the optimization right. Now, what we said basically is to have more parameters, and one of it is, for instance, C regularization that we will talk about now. From the outline, we are getting far ahead, so basically now we're really in the deep space, so to speak. Much more sophisticated models are possible with the content of this material that we will see here today. And we will end with really kernel methods which are still already cutting edge, right? So when you go now to a problem in industry, you will simply forget about the linear kernel we just used. We will mostly use RBF kernels. You will use polynomial kernels. There's a possibility to create your own kernels, right? This is a little bit tricky. You have to satisfy Mercer's condition, but it's possible and people do that. So this would be really the now in industry and everywhere in science, so to speak. While here, we start now slowly of extending the maximum margin. We add the parameter C. We go from a hard margin to a soft margin, and then could do this with a flower problem if you like, or use the Rome or the Indian. That's of course something now you can decide a little bit. Nonlinear transformations will be very important to understand kernel methods. right? They're kind of a leading way to it, not directly related, but following the same principles. That's why basically it's a very important thing to talk about this first, because then it's much easier to understand kernel methods. Right, so let's go. Let's think about the key principle, regularization. So we already told, basically in one of the lectures, it will be something like penalizing the model. Simple model better, right? That's what we discussed. That's very important. We're putting the brake, so to speak. And this was largely because we had the noise and we would fit the noise, right? When we continue training exactly according to every point, take every point by heart, so to speak, then we will end with this interesting notion. But, you know, regularization in a sense would be kind of this restraint fit that you see here. We take it more relaxed. We don't take every point, basically, very literally. And this is how you apply regularization. And you see with this, you have a much more function that is closer to our target function, that we know this very wiggly curve polynomial to some degree. And with this, automatically, we generalize much better. And this is the point why we're doing this regularization in the end. We prevent overfitting for a reason of getting better generalization out of samples, right? To get a better decision boundary, because no matter what happens now, we can be very sure that this model would be much better, right? Depending on which side you are, you would get better results than this interesting wiggly curve that is here and there, you know, still nothing in a way to do with the target function, which is quite a simple model as well. So this helps a lot when we apply this, and we go on step by step of thinking how we can integrate this in the SVM to have a practical example. So it's something what we will come back to again when we change now the parameter C, and when we change from the SVM to the SVC, based on the margin, to the support vector classifier in a moment. So there are basically two approaches how you can do this. Right? It's something where, again, it's not really something mathematically established of saying you should always regularization 0.5 or 1, or this parameter should be always set. It's now a kind of search, really. What could be the good regularization kind of value? However, the methods, how you do the regularizations are here, they're very clear. They're integrated in the algorithms. For instance, in SVM, the C parameter, as we will see, is integrated in the algorithm. When you see the neural network, or remember that what we discussed was weight decay, weight drop. This was part of the training process when you do the neural networks. Right? So it's part of the process itself. However, it's basically on the idea in generally that we basically work still on this error in sample here of picking the G that we want. And here and there you do some heuristics because this space is huge sometimes, right? Even if you have other parameters in combination with this, it's not just one regularization parameter. It could be several ones you use, right? In this sense, it's really a search where you go for, and this gives a little bit a problem of finding the right one. Why it's a problem of finding the right one? That is best explained perhaps here. So when you have here a kind of simple approach where you have here the error in sample based on some weights, and you have here the lambda, the kind of learning rate, or the kind of regularization parameter in this sense, you basically would apply that. This is just a toy example to make a case, right? So you again have our model, you do the overfitting, that's what we know. You do the free fit, not any regularization, right? And you see it's very terrible from terms of generalization out of sample. Now when you apply a little regularization, that might be very good. And you will see in practice that regularization should be really carefully done, right? Not really abrupt, like weight drop in the artificial neural network case. When you drop all the weights, then the neural network is not really a neural network anymore, right? You have to do, let's say, some compared with medicine, to give a bit medicine. If you drink all the medicine at once, then of course it will not work as well. Then you kill the training, so to speak. Hence, you could see the other way, when you do too much regularization, right? When you have a very big parameter here, you do a too simple model perhaps, right? So in this sense, you then also go more to the level of not overfitting but underfitting. Now you have a very much interesting target function here, maybe this one, but you have an almost linear model that not capture all the relationships in the data, just by applying too much regularization. So this is now the kind of chicken and egg problem that you have. You won't prevent overfitting. If you do too much regularization, you underfit. So again, we have to get this parameter right. And the choice of lambda here, in this example, that is the beautiful aspect. We have the validation. Right? To the rescue, we will see how that materializes in lecture 6, where we then look basically then to these values and see how we can have and find lambda in a kind of more systematic fashion together with other parameters. Right, so what does it mean in terms of other regularization ways? There could be early stopping, that's what we already discussed. In some ways, when you think about, for instance, the pocket algorithm or some ways in other algorithms, it makes sense perhaps to do this early stopping. Artificial neural networks, if you train them and train them and train them and never stop. You stop at some point in time, and it would be perhaps better to stop a bit earlier than later, because you will see that the model complexity will grow, the in-sample will go down. That is always the case, right, if you train more and more. But the problem is, again, as you remember, this kind of thing we are mostly interested in, the generalization error. The error out of sample of things we will never know, just that we know it's new samples coming in, and we want to make that right. So, of course, this is just one part of the story. Right? Takeaway message that we have regularization always goes together with validation. You don't use one or the other alone, in a sense. Right? That now would be a little bit too less of the medicine. Hence, we need really to fully understand this part. Also the content of the material of lecture 6, which is about validation. Right? But this is an interesting way of getting rid with many things with the stochastic noise and basically also deterministic noise, because both of them will be not taken so, let's say, literally with the regularization applied. So here's another example for choosing guidelines. So weight drop and weight decay is usually better than, let weight just grows. That is something which is, let's say, one example. Then weight decay, I was already alluding to in the artificial neural network, so let's skip that a bit. And this is basically something where you have to get, again, of course, the thing right. When you have no regularizer at all, this would be also very bad for then the overfitting. If you have the regularizer, you have to be very careful what you put as lambda. Start slowly and add this step by step with 0.000 something and see what happens. Right? So from the practical perspective. And a little bit this is alluding to the complexity of the model again. Again, simple models better. And what we sort of stopped in the Jülich-Sherman-Enkes inequality was then the next step with what would have been the VC dimension. That is usually standing for the degrees of freedom you have basically for your model. And of course this means something to do with how flexible is your model, how complex is your model. Artificial neural networks, very high orders of freedom, because I can choose my neurons, I can choose my input space, the number of neurons there, the number of hidden layers, lots of different parameters. The perceptron basically had just a W, right, a linear. Or support vector machines will have a kernel parameter and a cost, just 2 parameters. With this is also a handle basically on the model complexity, and the rule of thumb is really like Occam's razor. Simpler and smoother hypotheses are mostly always better. But don't overdo it, but just do always linear ones. Right, we discussed this example already with the video, right? You can consider here is weight decay, weight drops. It's not something just for, basically for support vector machines. You do the same in trees. You have ensembles of trees, this boosting, where you do then construct multiple trees in parallel. And here also you change here partly the kind of trees over the time, so that one learns from the other in a way that is also regularization. You don't need to understand now trees. I just want to take again the message. You can put regularization in all the different machine learning models, and you have to. Right? Without regularization, we learn too well in a sense, or basically memorizing rather. Now, when we come now to the motivation of support vector classifiers, this is now where we discuss the support vector aspect of it. And here we maybe want to shortly stop because it's a good time for breaking for the practicals. So I have already someone computed the parallel part. So what's the status there? Everybody is computing? Okay, the problem for you was solved?
No, I still get the error.
Okay, what is the error in that case? Just for the others?
Parameter is wrong.
The what?
One of the parameters is wrong. It should be C1 rather than C0.
The cost, yeah. Or remove it completely, yes.
Yeah, well, the default is 1. So.
Yeah, sure. Yeah, cost of 0 would be too strict, probably, yeah. I thought minus is definitely not allowed. I thought 0 is allowed. But okay, in this sense, then just skip the complete C or do 1.
And the M, do they have to specify -M with the value?
Yes, I think so.
Okay,
It's
there's
a
a value
memory
there.
cache. Yeah,
The value that's there is okay.
should be. Yeah.
I'll change the script and they can recopy it.
Yeah. Okay. So you heard there's a small bug in the script that I copied to you. You should need to specify the -C with 1, right? So the idea was to give absolutely no cost, no error, but this is something what we will learn now. So we were there already a little bit ahead, but the machinery there doesn't allow it. It's of course something which has dependency now on the implementation. So just do -C1, and for those of you where you get an error, it will work. Still the point will be that we have a linear model there, and the accuracy will be not that good. So we don't lose anything by just putting there a 1 now.
If you recopy the script now for the training, now it should be correct.
Right.
So just, if you can figure out the options, recopy it, and you can just use it.
Yeah, just check if your job has not stopped now, because we want to look on it later. So just check it now. We break here for half a minute. So basically you can use qstat, right? In qstat you should see that your jobs are still running. And if it's finished, then there should be of course a model file created. If there's no model file, that's an alarm bell. That means there was an error, probably with -C. If that's the case, please resubmit just by just correcting -C = 1. The model file was created? Yeah. Okay, very good. But you specified -C1. Perfect. Excellent. Good, okay, I think there's so many things now, as you see, around parameter C. It's time to think about what is this interesting fellow. And now the next 15 minutes I will just discuss this again and again. So again, we want to think about, this little outlier. If you think now what we learned in the maximum margin classifier, is a very good example that this guy is crushing us significantly in terms of the width of the margin. Right now, if you think about what this algorithm was doing, we maximize the margin, which is very good here. And just because there's this one stupid outlier here, we have suddenly a margin to the other space which is extremely small. Right? And this is of course something which is now very harmful for the maximum margin classifier we discussed, where there was no error allowed. Now, why not, and this is the case now jumping to the support vector classifier, why not allowing error? Right? And that is what you already do here in practice with C = 1. You allow error, you have a budget already for C, that's what you do. We just don't care about this outlier. I mean, firstly, if you have a data set like that, try to remove outliers, if possible. Right? But if you can't know that, if you don't know that for reasons, of course, and it takes time to look at the data and so on, there's a robust method now, which is basically the support vector classifier. So we introduce here something like we regularize in a way of saying, if there are situations like, for instance here, where some of the support vectors will suddenly be, or some of the fellows from one distribution lie on the right side in the plane, but they're in the incorrect side of the margin, right? They're not anymore in the space, they're inside there. This could happen, because then I'm not thinking this point alone is so interesting, maybe the others are. So you have a violation of the margin, but I'm still on the right side of the decision boundary. This is one case. And then, of course, you have the extreme case that we say now the outlier, in a sense, lies very much here. It is actually crossing even the decision boundary. It would be wrongly classified, right? Both can follow? Yeah, everybody can follow that these are two different cases, kind of. Right here, in this case, you could see that this is still something where the 12 somewhere over here moved suddenly over this decision boundary, or the other way around, 11, maybe happily sitting here, is crossing here even the decision boundary. Now, if we now in the very strict case, in our maximum margin classifier, that would mean a lot, right? When we don't allow errors, which means this now happening with the outliers, it's not anymore kind of linearly separable, and we cannot use our model. Hence, the support vector classifier is now the extension to this of actually creating then something which is more robust to these situations. So we can still use the SVC, the support vector classifier, by introducing now this budget C and some so-called slack variables. The slack variables are added up to your budget of saying how much error is allowed, right? So you kind of measure how far you're actually violating the margin. And this is useful because you have to have now a steering method of saying how much error you allow. Because if you're very, let's say, person that allows all the errors, then of course the maximum margin will suddenly cover all your data set. That is not helping either, right? So in this sense, you need to have this parameter slack. However, again, it's a rule of thumb, not a really mathematical established property, right? You have now a budget on your errors you allow, but this is again now a parameter we need in validation to be found. There's no exact rule saying your C should be always 1 now for all the support vector machines you do forever in practice. And we'll see how that materializes when we go to validation, when we do the grid search together. So in this sense, this is important to basically use this kind of C value with the slack variables. Another visual representation is basically where you see like this, all the violations that you have here, you know, the support vectors as we had before, nothing's changed there, except we have now violators, right? Here's a massive violator. He contributes significantly, basically, to your kind of budget. Then we have here smaller violations, we have no violations, right? This is still okay when you are on the, let's say here, the boundary of that. And these actually don't care at all in the regularization, in the amount of data points that you have, right? So this violations of the margin is now something which adds up to the C value, and you bound it by the C value. And once you bound it, you allow not any more errors. So from being open-minded, of extending to misclassified points, to kind of points which are, you know, always crossing also here the edges. You allow it to a certain point, but once your C budget is used, you don't extend anymore. No more misclassifications. Right? And with this, you become very relaxed to this kind of things which we see here a little bit. Where, for instance, here if you have C too large, that is not good. We discussed this already. But here in a sample, we have a decision rule, which is in a sense very nice, a good margin. We have some outliers, but we don't care. Right? They would contribute now to your cost. The same here, it's a blue point on the wrong side, and here's some violators. But still, this model would be much more better in practice than this large model, and would be much better than having a very too tight model, right? That we would here have on the other side, right? If you now do a very strict approach to this, right? You are back almost to the perceptron in a sense. You don't have a big buffer zone, right? In this sense, you kind of come back to the point that this doesn't help. So what actually is changed then is mostly that you put in here this interesting parameter C, and with the kind of slack variables you have, you can now see how much this really affects your kind of parameters. And the interesting thing is C is here searched in a principled way. In lecture 6 we will do that together with cross-validation. But what you also see is it's differently implemented here and there in the packages. Some of them bounded by value C, some will do multiplications of C, and with this basically have to kind of make the order of magnitude of how much these errors really count into the game. And this is the idea now of this magic parameter C that you all the time see, but we didn't use yet. However, from the global perspective, how we use the machinery, nothing changed. Right? We have support vector classifiers now. It's still inherently quadratic programming. Right? The mask changes a bit, and the derivations, which I don't put now again here, it's the same simple idea of the geometric interpretation. All you do is you allow some errors. Are we done with this? Are we happy? Everybody seems to be happy with this new model? Okay. No, but if everybody is happy, then I basically can go home, or we finish early. No, of course, think about their these cases. Right, now we have a very, let's say, open-minded model and would say, okay, decision boundary with some errors, and here are some errors. Let's put a decision boundary like that. Would that help in terms of generalization? No, right? So we see again a limit of this model. Firstly, mostly because we have still in a way a linear decision boundary in the input space. So we want to come to so more interesting, sophisticated models is actually not easy. There's a way how, for instance, artificial neural networks can do that, right? With different perceptrons stacked up in the hidden layers. All what they do is they contribute with all their linear lines, so to speak, from the perceptrons to approximate this thing. And they could do that, the artificial neural networks. Just as an example, it must not be support vector machines to go to the interesting linear, non-linear decision boundaries. Right? So this is an interesting thing. Still, we see now the support vector classifier has its limitations, basically in practice. Hence, when you go now to the job market, you will talk mostly about support vector machines and use mostly kernel methods. It will be the next part, but before we enter this, I would like to take a little bit time now discussing what you basically have in terms of your results from the training. So, what's the result largely of using parallel computing with Indian pipes? Some people have experienced speed up. Yeah. Right, and if not, please improve on number of nodes. Right, for instance, in the prediction case, it could take long. If you do there more nodes, you will see it will be a speed up. Right, and the same for Rome, and so on. And this will be available to you also after the lecture. As I said, there's a UCI machine learning repository with much more data sets also. You can try, download those, work on this at home. Because just this tutorial now, in a hands-on fashion here, it helps you just to get the basics. When you want now to really understand it, you basically need to, get more and more practice use. So with having this parameter c equals 1, hence we had already cost there, right? So that means it explains also why the lib SVM in the beginning had already a little bit better accuracy already, because it was automatically the SVC. In a sense, this maximum margin classifier that we had in the beginning will be mostly not used. It's a development towards the more sophisticated models. Okay. So for those that trained the model and did not test yet, please do the SVM predict now in parallel. Right? If you don't know how to do it, you use the other job script and use a model that was generated before. So this is it not clear to anyone how that exactly works? Then please raise your hand. Otherwise, I just proceed with the theoretical development towards kernel methods. Or any questions, perhaps, before we go ahead with nonlinear transformations? Going once? Twice? Okay, if that's not the case, Kenneth, I hope the cluster is really heavily working now, and there are lots of jobs, so that the people really actively use this. And of course, it will be still available after this lecture, right? But then the reservation will be gone. And so think about that now is a good time to test lots of things out, because we have a reservation, you can increase the number of nodes. When you're back into the production mode, so to speak, you kind of here and there in the normal scheduling, which means everything takes longer to be scheduled, especially if the number of nodes increase. Right? If you have bigger problems, you usually are not backfilled, then it could be taking longer. So use the time now, play around with the job script and actually do training and test on Indian Pines, different versions. Do the Rome data set as well. Right, so the next topic, nonlinear transformation, is interesting because it basically gives us and paves the way to understand kernel methods better. Who has performed nonlinear transformation on his data set, perhaps? Some of you are already in data analysis. Okay, right? It's a kind of feature engineering idea that I will discuss a little bit. And then we do the next step towards kernel methods, which is a little bit more elaborate. So basically what we said, like, we ended off with this interesting discussion that, of course, we have sometimes data which not really fit into a linear decision boundary. So we want to get more sophisticated, non-linear approaches. However, we can also think about that we can touch the data and transform it, and then work further on the data. And this is a context called non-linear transformation. So you basically take the samples here and transform them in a non-linear way to get a better decision boundary done. And this is a possibility that you can do when you, for instance, see this simple example. Right? So in a sense, you have now this big idea that I had on the previous slide in a very small scale idea. It's the same idea, right? You have a problem that in the middle is somehow a cycle required, and you have the example sitting out of this. So how I create this really? So we introduce here for this a phi, and this will remain with us also in the kernels. Basically a phi function that works on the data in order to transform it. Right? And this is something which is almost like computer scientists do daily. You know, you don't just put in a function phi, working on all the samples and do something with it. So what could that be? For an example here, we just take the kind of square from it. You see that all the samples that are basically here are suddenly from 1 and 2, they're basically here, you know, landing on this side. And this is the same for -2 here, those, they all basically go in this point. Now, having done this and changed basically the constants, and we can do that because it's our data set, it's our data set that we have in hand, we're changing just constants, right, for the learning algorithm that is independent from that follows afterwards, right? So this is something what we do in terms of feature creation, in the sense of saying now it's much more easier to do. However, this is now a specific space we call Z-space or feature space, which should be handled with care. Firstly, you see the inverse of that is not really any more possible, so we cannot make very many statements of saying, okay, what type of sample was not exactly the support vector? Was it this one, was it this one or that? No, all of them, you see, ended up in the 1, 4. And it's very hard to judge now from the original data, oops, this is now my data. If you want to explain your data a little bit, you can become into trouble. Also, if you overdo that, now you can overdo it in a sense of saying everybody gets its own dimension of the points. Right? That would be the easiest thing to do. Right? Then you have a very sparse dimension set where everybody has its own dimension. And of course you can do the different boundaries between them, but the generalization then, when you think about the simple problems, would be then in question again. So again, we have here a mechanism, there's nonlinear transformations, which are, in a sense, and to be handled with care. One example, however, where you think it could maybe happen, is again here, where we think about that we just go basically from this two-dimensional case that we have here to a three-dimensional case, and then introduce something what we call a decision plane or hyperplane, right? It's not anymore a line, you know, in the multidimensional space. So as I said, we go more sophisticated now. So that means this is not really possible, but when you now think about the SVM will work also in the higher level space, here for instance, you would just simply create a plane here, and suddenly those are again separable, right? Just with a plane in the space. And that is actually how then later on the different algorithms will work. And you can do this now manually, right? You can go through the data and kind of apply this rule that you see here, just go from 2 to 3 dimensional. Of course, you have to a little bit see in your data if that really works. Depends on your data set, extremely heavily, right? So this nonlinear transformation is something which you have to really look on the data. Hence, it's a feature engineering technique before the classifier will work. It's nothing to do per se here now with support vector machines. So connection we will do in the kernel methods. Right, and this is how it looks like. So now we basically have done this. So we use the support vector machine in this new data set, which is now 3-dimensional. The support vector machine will do the same thing, even in the higher dimension. It will find the best plane, right? With support vectors lying here and there. So instead just of a boundary that we had in the 2-dimensional case, we have a plane. Doesn't hurt us, right? Because when we map it back now, basically back to the input space, when you project that back, you would have something like this now created in the z-space, in the feature space, right? And this is of course a mapping, this is also handled with care mathematically, because in a way this phi mapping is a one-way street. For instance, in this example, when you think about these, you know, you lose sometimes here and there the identity really of samples, but it depends on your concrete nonlinear transformation. But this is just an interesting example, and you can here have really the problem that when you go too much with this, right, it is called the curse of dimensionality. If you think about really each of the points gets its own dimension, you can always do that with an interesting formula, right? x1, x2, up to xd, wherever your problem is. And then you have a very sparse space, nothing anymore, you know, saying you can divide them perfectly, but the generalization of the next points will be not really very good. And this is basically just a short glimpse on nonlinear transformation. Everybody has understood the idea in general. Right? We shift the view now. We are not in the machine learning algorithms. We shift the view to the data samples. Nothing to do with learning. We shift the data, massage the data, we will sometimes learn nonlinear transformations. Good. So kernel methods now will make the connections of doing this internally inside the SVM, because if you remember, we had this interesting dot product, right, which was just depending on the samples and the mathematical development of the geometric interpretation. We ended up of saying the decision rule is in the end just a dot product, and then we also ended up in the optimization process of the Lagrangian, it's just a dot product of the samples. So when I now transform the samples and say they are valid, and there we will come to the point what valid means, we just can stick in other data. And this is actually what we do with the kernel methods. So in a sense, we plug in the idea of these nonlinear transformations, in a sense, with the kernels into this support vector classifier. And in this sense, we don't use anymore the linear kernel, which makes it automatically the support vector machine. Now we're talking, this is a real official support vector machine. Before it was just support vector classifiers and maximum margin classifiers. So when you now in practice in job, I'm a university professor, so I have to be a bit more on the terminology accurate. When you know on the job, right, people will not care about this differentiation. It's just a mathematical development to take you step by step to a more sophisticated model. When you're in practice, you will talk mostly about support vector machines, right? But however, in practice also, what I discussed, you will mostly use kernels. So I rarely see anywhere in practice that people don't use kernel methods or linear models in support vector machines. Perhaps they're sometimes better off of creating than other linear models, like regression or some studies. Right, so let's do that. For that we have to go a little bit back to the mathematical development we had, and we left off with this interesting equation, which is in our case now just a dot product of the samples. Right, the rest here is our labels, and we want to get the alphas back from the quadratic programming package. So when we have this in this kind of optimization that will take place happily in the QP package that we get, like libSVM, we have it also in the decision rule, right, which is also interesting. So this is a kind of development where we see, now when I change something in the optimization, that's fine, but I would be in danger if I don't change this in the decision rule. Right? So what we do now is basically just do a kind of computer science approach. That's how I explain it to the statistics people that I have in my courses. You plug in another function, and that's really the kind of kernel trick. And you kind of use just instead of the typical dot product, you define a function, you put in I and xy, have the kernel defined as this transformations Similar as we discussed basically now in the nonlinear transformation case. You have now a specific function phi that is supposed to work on these samples, right, that we have. And we can always do that. That is our in-sample data set. We can work on that. Similar for the decision rule, the same way. Before you do the decision, right, of saying, am I on the right side or on the left side of the decision boundary? You remember that is depending on this projection here. We firstly plug it in to the kernels of saying, here, this is a specific function phi you firstly have to go through. And then with this, you're a little bit like the computer science approach. You just actually use the data with a function instead of just using the data itself. And this is an interesting aspect called the kernel trick or kernel methods we will discuss now, because it has interesting properties with it. And of course we cannot go into extreme detail with it, because then we have to do Mercer's conditions, how to create kernels and their validity, because you cannot just simply put any kernel. That's a disadvantage. There have been some people already creating some kernels that we can use. Right, so the idea is here nonlinear transformations basically, but in a way we have seen when you do that extremely, you have problem of course of dimensionality, it doesn't help us so much. But the idea is still the same as a kernel trick of saying we're creating a, for instance, higher dimensional feature space just using any phi, and we will talk about which phis they are. And then we use in this feature space our typical machinery or machine learning, right, of our maximum margin, including violations of the margin. So I can always do that. It's in the Z space or the feature space, and I solve my kind of typical problems there, and it's all valid. However, I'm still in this Z space, right? And let's see of the kind of ways how you can do it is basically the kind of dot product. If you remember what it is explicitly, it's like the sum of the different points, but it's this really just the aspects that I just talk about a little bit more longer elaborated, which means an interesting property that also reduces the data in the end. And this has something to do with a step also that kind of you have only those which are support vectors in the end. If you remember from the quadratic programming also, those will be mostly 0 for non-support vectors. So we're talking basically about those, because most of them will be 0 coming back from the QP package, or almost 0 point something. And you basically just have them at the end here kind of the situation to do only on the support vectors. So you reduce kind of the amount of computing that is necessary with that, right? Because the others don't make sense to look at all, because they don't matter for us still, right? And this is an interesting aspect. And now that was also the breakthrough of the kernel method, that we can plug that in. But now is your point like, okay, what can I plug in, right? Just saying there's some k, the function doesn't help us. So what we do here is basically we plug in now different kernel types which are already existing. One you have actually already used, right? The typical dot product, which remains linear here, right? But you just do it now basically in the feature space, but it remains the same. So it's a linear kernel. There's no change, right? Now the interesting thing is now there are some other people that have already done, other aspects, like for instance a polynomial kernel, which will now take your data and add it to some polynomial of some degree. Hence, the kernel gets a parameter d for the dimension, right? You now have to steer what dimension you want for the kernel. And this is one of them that is used in practice, for instance. A polynomial kernel, depending on what your data is, could be interesting to use in real practical situations. While I said the linear kernel is really, in a way, very rarely used, and of course no win compared, in a sense, to the support vector classifier that we had before. It's a linear decision space. So the kernel trick is just nothing else than plugging in the case in for some of them that have been well established. Why I say well established? This is something that people have, analyzed this, and there's a certain recipe that you have to follow called Mercer's condition, right? Only those that follow this specific condition are allowed to be kernels. But when you create your own kernel, you can do that. You have to follow this recipe. But this will take basically another lecture to go through. That's why I leave that out. Hence, you cannot just use any kernel, right, and implement your own ideas. You have to use those which make sense to fulfill this condition, otherwise your machinery will fail. However, it's not so bad that we only have the polynomial kernel that was already established by experts that we can use as a function to plug in. And you will see the libSVM actually supports this, and also the PySVM. There are also more advanced kernels. So, but what is the trick with all of this when you think about computation? I have a small example here. It looks a bit wild, but it actually is not so drastic. All what we do here is an example for the kernel trick to show that we need very little computing in the transformed space, right? And this is the interesting thing. There's no need to compute the mapping directly, right? So what would you think would you do now first when you think about this? So when you have now a function that should do this, phi, and this is a transformation of these. Now you would compute the mapping directly of saying phi on every xi in my whole data set. Right, so that's lots of computing. So I have transformed all of them, go through all the data set, 1 times n. Now I do the same thing with my other dot product fellow, another thing. So this is already lots of compute time, right? We have to do it in a sense because my kernel says I should do it, to transform it like this. However, the interesting thing is if you have this kind of machinery and you put it then of course inside this optimization step, right? So it's inherent in the Lagrangian and the QP package. Still, what will happen is if you define k equals, if you have a typical function in computer science, in C, also you define a function, please do this and do that with your kind of function. You plug that in, then you would assume, okay, let's do all of this first. But the interesting thing is, like, when you have defined a kernel in a specific way, you see that some things maybe just fall out. So when you do the transformations here, and perhaps firstly do all the math here, basically before converting and doing the mapping directly, right, and doing some mathematics of the properties of the dot product, the interesting thing is after some chain of mathematics now really, right, it fills a page, but you can actually do that at home if you want. Just do little by little, step by step. Just the interesting aspect here, you will see that it really rules out all the transformations. So what will remain is something which is not dependent on phi. And this should basically now an aha effect. Right? So we visit, what does it mean? Means we define a Z space, anything, but actually we never visit the Z space because we can compute it directly. If you do the whole chain of mathematics, you will find out that it's not needed. And this is a kernel trick which is actually, you create a fancy Z space in a sense that you never really visit. Right? All what's coming out is then the kernel in the end, in this particular example here, computing this, which is very easy to do, instead of doing first all of this and doing first all of this phi. And this is kind of the idea of the kernel method. That's why lots of computing time is actually saved with this. And of course, in the transform space, it's still a dot product. In the original space, there's firstly no big kind of computing needed, right, before you give it off. And that's the interesting takeaway message of the kernel. Right, so there's the polynomial kernel we discussed already, which is, allowing much more nonlinear decision boundaries you can assume. And of course, this is something what you have to also pick then when you have, of course, a d to the 1, you're back to the linear space. Now the polynomial kernel should be really used, and you see in the libSVM now on your snapshot that this is actually a kernel parameter, right? When you come now, let's switch shortly to the practice. We had the idea of looking at the libSVM parameters, and you have the polynomial kernel right here, right? With the interesting kind of function here, and you put it to some degree. Hence, you see the degree, the set degree in the kernel function is one of the parameters. That's not something where the mathematics will tell you exactly what to do. You have to think now how to pick it. You do validation for it. Hence, topic of lecture 6 then. And right, with this you have a higher dimensional space, you do basically the kernel transformation in that Z space, do the typical support vector machinery, and then you can report it back. However, also in the break, someone already was asking me how you report it back. This is of course something you have to look at. And here are just some examples what a polynomial kernel can do. It is, can, you know, instead of the kind of typical linear where you would think these will fail, we already said now with this new machinery we do a similar thing like we have done before in the nonlinear transformation, but now it's part of the optimization package with the kernel, with a trusted kernel I should say. And then you can, for instance, to this decision the boundary, and you see here the degree is 4, for instance, and here's the C parameter, so we allow some errors, and so forth. But of course there are more kernels, and actually if you now look in the literature there are very many kernels, but the most used one, I would say, in most of the applications is very often the RBF kernel. The radial basis function kernel has an interesting property and goes back a little bit what we had yesterday already with the clustering. A little bit is the interpretation of having a local behavior with the distance function we already know from yesterday, the Euclidean distance, used basically as part of the classification. And with this you can have interesting boundaries like this, which are, you know, very nice and could be very accurate to the point in the high-level feature space, right? You plug again this rule, which is the kernel parameter here. And however, the problem comes to us, this fellow, right? We had the polynomial kernel with parameter d. Now we have the RBF kernel with parameter gamma, which essentially steers a little bit how big is your distance and how you kind of tuning it with this, right? And this is an example of the large and small, tiny distances, not so important. But the important thing is that we need to specify this, and this will be of course something which we again put to validation. We search for it in a systematic way, but now you will see, okay, we have C already to be searched in a systematic way, and the gamma to be searched in a systematic way. So what do you think about this? We have two parameters. We end up in a table now, right, to find the best parameters. And this will be also a part which we have in lecture 6. We now have to think about the more parameters we add here, then the more multi-dimensional gets our parameter space to search for the best parameters for our model. Hence, much more computational complexity. You have to test all the, or validate all the different models, and this costs lots of time, and hence it's even sometimes not possible. You use things like particle swarm optimization, go the best way, things we discuss a little bit in lecture 6. However, put the focus back to the radial basis function, which is this interesting fellow, and let's go to the practice again. When we see your libSVM or our pSVM, it doesn't matter, both have implemented this kernel, which is basically here, the radial basis function is minus t2, right? You just put minus t2, but it also means when you specify this, you see the parameter gamma here, you have to specify minus g gamma, set gamma in kernel, right? Because you see also here sometimes are, let's say, some defaults, which are also rules of sum. So if you're in doubt what gamma should be, then you're sometimes good and have 1 divided by the number of features. So some rule of sum are already helping in the game, although in a systematic fashion we will find them with validation. Right, and with this you have a toolbox now, right? As I said, you can create your own kernels and satisfy Mercer's conditions, but my chances are very high if you use one of those in your kind of problem with SVM, you have a very good chance to actually have a good result happening. And if you don't get really good result, the failure might be somewhere else. So before you potter off and create your own kernel, I encourage you first use the polynomial kernel, or mostly perhaps firstly the RBF kernel. Don't forget the gamma and the d for the different, let's say, parameters. So what we have now as a kind of summary, we have now the really full support vector machines, which are called this way only if there are kernels inside, right? Really kernels that put the non-dimensional property with the kernel trick into action. The whole idea of the algorithm of quadratic programming, sequential minimal optimization, doesn't change with it, right? So it still works on the dot product in this sense, but of course in this interesting way that lots of these computings doesn't take place through the kernel trick, right? That we had in this small scale example. When you do the mass first, instead of transforming first, you will see that lots of these things can be avoided. And with this, the kernel trick is really successful. Right, here's just some ideas that you can also transform, let's say, non-linear transformation with this in the Z-space. In a way, it's what I did already said here the couple of times. You can basically see it very similar, but don't overdo it. If you have a very long million D vector, this would be very, very dangerous to do. Hence, with the kernel trick, you see, of not doing this per sample first, but let the kernel just sneak in, and then in the process you see you don't require the computing, actually in this part of the game, in the process, right? Then you basically have then the win of the computing time significantly reduced. So the challenges in this infinite spaces would be then a little bit related to this, but in the matter of time I would go a little bit quicker now through this, because here and there we're touching on the things of the example that I had before, and I think the example before is already, of course, clear. You have to go through all the different kernel aspects. You have several spares there and elements, but several of them will, kill each other in part due to this quadratic programming property. You will see several ones of these will be really, dropping and so on, and not really computing. Right, so perhaps more interesting, because many people came to me in the break and were saying, how do we know the decision boundary? We have done this trick, right, already in some of the graphics. So how do you visualize that? If you're in a Z space that is unknown to us, infinite, as we just discussed, we have any phi, according to a trusted kernel, how we actually visualize that back. And this is something which a bit leaves mathematics again, because this is basically a one-way ticket, right? We have a function that transforms our data as part of the kernel method, do the kind of separation in a high-level feature space, do there's a separation, and what we do now then, basically we map it back on the surface. And this is the perfect property of the support vector machines. And why is that possible? Any idea? The support vector machines are in sample. That's a key property here, right? The interesting thing is we would say, okay, maybe that's overfitting in a sense, but that's not really true, because we did it in a systematic way with the best possible margin in the Z space, in the feature space. All we do is those fellows we identified as support vectors in the Z space will remain data. Right? They're just transported in the Z space. The identity of the data itself is clear. So we can map that back, and this is where a little bit mathematics is, not really defined at that way, how you do the mapping back. But from our visual expression, that's how we can interpret the multi-dimensional high-level feature space separation. Because if you just map it back, all the support vectors, they have some of the red side and you have some of the blue side, you will see that this is a perfect linear decision boundary that generalizes very well, because in the feature space you have this particular property. Of course, it looks a little bit in the input space like I have now a very wiggly curve and the next would be misclassified, but of course you have the kernel again to transform to the Z space, right? Also in the decision rule. So this is an interesting property, what we now should really do in practice. So now it's basically the time to again looking at the regularization parameter gamma, perhaps try out the radial basis function kernel, but if you want, you can also use the polynomial kernel in your tool. And as you see, it's really just playing in your job script now with very little changes. You still need the training, right? The training set for Indian times, we change nothing on the data, but the kernel will do that for you, right? With this interesting kernel trick. However, we have to specify this. So instead of using now -T0 for the linear kernel, we learned we can use polynomial. If you use polynomial with -T1, you have to add minus d for the degree, right? Because they go together. 1 minus t1 means you also have to specify minus d for the degree of the polynomial. Also, equally, gamma is needed for the radial basis function kernel. So when you switch to minus t2, you also have to specify minus g, your value for that. So for instance, pick 8, 16. In the next lecture, after a break, we will see how we actually pick these parameters systematically, right, in validation. And this will be then the counterpart to the regularization to finally combat overfitting and get a very good accuracy in a very good model. Right, and of course, if you want, you can switch from Indian Pines back to Rome, because in Rome we did not have very good accuracy, or some of you, as I had also heard from the break. So now with the RBF kernel, if you use that on Rome, there's much more chance of a high accuracy. And all you have to do is, of course, just using minus t2, and for instance specify then gamma 8, 16. However, how we pick gamma and so on is still an open question mark, and also how we pick the cost c that you have to specify, right? So this is something again which will come in lecture 6, but now is the time, I think, to a little bit go back and think about a break before we come to the other parts. Perhaps shortly, as a kind of explanation for multi-class classification, the whole theory that I have shown is mostly based on two classes, because the mathematical way there is mostly friendly. When you're there, you can also prove that all that works basically in the multi-dimensional, multi-class setup, right? But this is of course more math, more mathematical development, which doesn't, add insight here in this tutorial. But take away the message that SVMs cannot do that margin only, let's say, for two classes. It can do that for multi-dimensional. So how you do that for multi-class? So how you do this is largely depending on two different methods, where you kind of have a similarity, for instance, like voting, right? So it would basically first go one against each other or one against all. So let's look briefly into it. That, one versus one, all pairs classification, and what it means basically, for instance, if you have a 52 class example of Indian Pines, it will create 51 decision boundaries now, right? Because the idea will always be the same. You have a perfect plane separating, but the question is now what you separate, one to one, one versus all, right? And this is an interesting thing. Think about memory. You need much more memory if you have a very multi-class problem, right? And this is an interesting aspect, and there are two kind of ways how you can do that. The one is here basically thinking about all pairs 1 versus 1, and you count the number of times that each was assigned to some certain classes. So it's like a simple counting, voting in a sense, of how much was this often put on this side or on the other side. Then the other approach is this, and it's really, we have to be, if you really want to go deep into that, I would recommend a book, and looking that it doesn't add insight here too much, and we don't have time to really specify all of this explicitly. But then you have, of course, also the one versus all classification, which means you basically have really lots of these models available inside the memory, and then you're basically counting again where, in which areas your samples fall. And by simple, averaging out over time, you will basically have then the kind of assumption that this point would be mostly in this particular class, depending on where it falls in the hyperplane space, right? You have multiple decision boundaries we're talking about now, multi-class, right? And of course, this depends a little bit where they fall, and it's not something which you can easily bring across, let's say, in a small tutorial like this. Just take away the message, SVMs can do multi-class and very effectively, and do that largely, for instance, if you want to take away the message by voting. Right, so here's a small video that I brought, bringing again the idea of the kernel trick and the polynomial kernel if you want. And then we really break for a small example.
Does it have sound?
No, there's no sound. Yeah, it's just a very simple, tiny example that we have seen already on the slides, right? But you have a problem like here, there's red and there's blue, and all what the polynomial kernel now does, in a sense, is bringing it to a higher level feature space, right? Increasing in the dimensions, like we have seen in the 3D dimension example. And now what the optimization process will do in this high level feature space, it will just create a hyperplane. Right? And if you have now another class to it, basically it will do things back. And what you can do now, as I said, in completely not correct with inline and math, you can map it back, because in the feature space, the identity of the data is still the same. It's in sample, the support vectors. And that is a key property why we can understand that so well. Right? Where we can really take assumptions, this particular data sample contributed to this model. When you think about it, you have 100,000 samples, right, in the list, and you want to have those which are really important and, you know, characterizing the SVM, you would pick your support vectors. It's an in-sample property. And with this you can see when it works well in the high-level space, like these points here, these are support vectors. You move them back to the space here, and you have still the link because they are in-sample. You can come up and say this is basically the decision boundary we created in the input space, although we do it, of course, in the feature space. That's a very advanced topic. I know. And of course, this is like an introduction to machine learning course. So there are whole courses just on kernel methods, right? And how you create kernels. Again, Mercer's condition to look at this. You have specific properties to fulfill with a kernel. You cannot just invent your own kernel and say it's right, as you can assume by the kind of properties it has. Right. So with this, I think we're ready for a break, unless there are some burning questions. There's one question, yes?
So with regards to the choice of using one versus all or one versus one, the guide which one is better?
Usually it's already implemented in your package, I would say, so you don't care about that. So usually libSVM, for instance, has everything. Usually you don't specify that.
Yeah, I don't see the options there.
Exactly, there's not an option. That is a little bit some inherent saying just for you how it is done, because we always had the two class examples. I wanted to bring it for you just that, of course, all the theory you can see that it is established for the multi-class. It works the same way of doing a hyperplane in the higher space, but you have then, let's say for 52 classes, 51 models, for instance, that you compare against, and then with voting, we'll see where is really the point there. But you don't see that, your package. And no matter where you go, MATLAB, R, the serial packages as well as the parallel package normally don't have this as a normal configuration option. I could see that maybe if you go into the code, you can probably change that here and there and create your own strategy, the one or the other. But I think normally that should not be a real concern for you starting. It's really then an advanced topic if it really makes a difference. Any other question maybe? Going once? Okay, yeah, please go ahead.
So you have talked about the testing and the training data, like this 10-90% division. Is this something similar to the k-fold cross-validation?
Yeah, interesting question. So the question was for the online audience that we're talking always about training and testing, and particularly at here and there say we take 10% only for training data and 90% for testing data. Right? And then the follow-on question to this is this related to cross-validation, right, or validation? So in a sense, no, not really. It is a directly other established part. However, of course, it has some relationship when saying, if you're swimming in data, this would be a good thing to do, of saying 10% for training, 90% for testing. And when you then have some samples to afford, put in a validation set. Right? So this is something that I would recommend. It has to do now with validation, cross-validation, in the way that we have not so much data, we're not swimming in data. That's a problem in science and engineering. We have less ground truth, less labeled samples. So in this sense, it has relationships to cross-validation in the sense that we save the validation set, and this will materialize in lecture 6. We save this whole data set that we normally put aside for validation and can use a training set for validation, which is normally bad, and I will make a point why that is bad. It has to do with data contamination and learning from data for model selection, which you shouldn't do. But this is a point that you can use this 10% in a sense with cross-validation then to do your model selection. But it's hard, basically we don't have the really fundamentals now what validation is in general. That's why we basically need lecture 6 before we perhaps answer really questions like that. So we need the fundamentals of validation first, because there's a trouble of picking parameter k, how much goes to validation, how much to training, how much to testing. Right. I hope partly that answers your question, right? And I think in lecture 6 we really need to go through this first, and then we can answer questions like that. Any other questions, maybe? Going once? The kernel trick is clear? Going twice? Okay. If that's not the case, should we say half an hour this time, and perhaps a little bit longer, coffee, and we continue for simplicity just at 3 o'clock? Right? Okay. So see you at 3 o'clock then. This is the final lecture. And in between, feel free to use the machinery, right? Change the data and change parameters. So experiment with the system as we just did with the different kernels.